There is this big race going on internationally of getting a well-working quantum computer and a large enough quantum computer to do some real important calculations, problems in artificial intelligence, machine learning, finding new drugs, synthesizing new chemical reactions, but also searching big databases and finding quick solutions to optimization problems. So here in New Zealand we have a strong heritage in quantum optics, which is one of the basis for quantum computers. We have a number of researchers working on this field, and we are able to provide an enabling technology to provide networks of these computers, and thereby just increasing the complexity such that they can tackle the real complicated problems. There is currently no way available to connect two different quantum computers with each other. So you have this problem that you have quantum computers which are great, but you cannot connect them. The current superconducting quantum computers are based in a cryostat where it's very cold, and you need to be so cold because these systems are interacting with microwave photons. And a photon is the smallest bit of energy possible. You have these two different quantum computers wanting to communicate with each other, but they can only whisper. And the whispering is like whispering into a very loud and noisy room, and so this whisper is completely being lost. If you want to go through a connection at room temperature, you cannot use microwaves. And so we propose a conversion into the optical domain where there is no noise, and we can just connect these systems through optical telecommunication. To convert the microwave photon to an optical photon is really difficult because they're so different wavelength, and it really doesn't happen in nature, and we figured out a way of how to do this. So the method of upconversion that we use is based on an electro-optic effect, which has been around for a while, but we managed to increase the efficiency by 10,000 times, and therefore getting it into a domain where you can actually have individual photons being converted. So to do the microwave to optical conversion, we need to have the microwave photon communicate with the optical photon and really interact closely, and this mediation between them happens in a crystal, and the best way to do this is to actually shape this crystal in a round structure so we can get this green light into the system, and that is nicely confined via total internal reflection close to the rim. And then we put in our microwave, which also is confined in this area, and so they can interact with each other to generate a new other optical photon, and this upconverted signal can come out and be transferred in optical telecommunication fibers to connect to another quantum computer. Here I have an example of one of them, which is just this transparent device in the middle. We make these devices, and we are one of the world-leading groups to make these systems. This big casing around there is to confine the microwaves, which just have 10,000 times longer wavelength, and we can close this package once we have everything set up properly, such that you have this little tiny device where both the microwave signal gets in, the optical signal gets in, and the upconverted signal gets out. So our proposal to do this upconversion is very well received in the world, with a number of groups copying the idea and by now starting to enhance it in different systems. A few groups in the United States at Harvard and Yale, and they are currently working on it. So the Dodd-Walls Center is a great incubator of ideas. My colleague Jevin Longdale at the Dodd-Walls Center is working on the same problem with a different physical system, how he wants to tackle the problem of upconversion. And so the Dodd-Walls Center really helps us brainstorm ideas, talk to other scientists in the field, and provides the students to do this work.